This video is part of a course on food physics, of which this one is in the application section. This one on air drying has 5 videos in this series for air drying, and this one is the 4th video. This is one of the 3 videos talking about 3 different approaches to understanding the physics of air drying at different levels of simplification. This one happens to be the simplest approach to describe the physics of air drying. The 2 videos before these described in progressively more complex ways of describe or more mechanistic ways of describing the food physics. So here we introduce a very restricted and simple model, so simple that it is almost empirical, but it is used extensively in food drying, so it is worth talking about. Now the learning outcomes for not just this video but this series of videos on air drying are here. We have described in detail in previous videos. You can pause the video and read the details. I will not get into more. So of the 3 approaches to studying the physics of drying, we are going from more mechanistic to less. So the video before this one, we talked about the diffusion model approach to studying drying, and the video before that had not just diffusion but also pressure driven flow. But right now we're going to be doing the simplest approach to studying drying that has been used extensively in drying, but it is really for a very restricted situation. In our previous video, we have described a diffusion-based drying model where there is significant internal resistance, and the process can be described by the diffusion equation where D is my diffusivity of moisture. Now, there are special cases where the internal resistance can be small compared to the external resistance. It's never zero. It's small compared to the external resistance. In those cases, we can ignore internal resistance and think of the entire inside to be approximately at 1 moisture level at any time, and that would give us this equation that describes the physics, which is the topic of this video. You notice that in this equation, this one, here there is no x. It is not a function of position because we are ignoring that. That's what we mean by a lumped system where we're ignoring variation inside the solid internally. Now, we are going to derive this equation from scratch in the next slide, but if you are mathematically minded, you know that by using Green's theorem, you can mathematically get to this one, and we don't have to derive from scratch. So when can we ignore internal resistances? So if this is a slab, and let's say the thickness is L, then L over dA, where A is the surface area here, is my internal resistance. Okay, and so when is it small? So if I have a thin material being dried, then it doesn't take that much effort for the moisture to diffuse from the innermost point to the surface. So this is what we mean by small internal resistance. So let's look at a little more detail. When it's thin, L is small, so the resistance, as noted here, this one is small. Another one is if the material is highly diffusing, if the water is highly diffusing, then the diffusivity is large, so that again gives resistance to be small. So let's try to compare this internal versus external. External resistance here is of course convective resistance, outside resistance, and so this ratio, internal diffusive over external convective resistance, is called the Biot number, and for mass transfer it's written this way, which is same as for heat transfer, except we have this K star which relates moisture in the solid at the surface to the outside. We will spend more time on it. So this ratio, when it's less than 0.1, then we say that the internal resistance is small. That simple equation is now derived here using a simple mass balance. So consider a thin slice of potato with airflow over it, for which we are going to do a mass balance. Okay, so our mass balance always is written as in minus out plus generation is change of storage. So let's think of the potato slice as my domain on which we're going to write these individual terms. So in, if potato is moist and the surrounding air is dry, moisture is only leaving, so in is 0, then out is by convection. So out is this air carrying it away. So its mass transfer coefficient multiplied by the surface area here, and concentration of vapor at the surface in air, though at the surface but in air, and concentration of vapor at infinity, which is far away. Okay, so it's the concentration difference. So this difference is the concentration difference of water vapor between the surface and the surrounding fluid. So this is the surface vapor, this is the vapor at the surface, and then the surrounding fluid. And so that will be the flow rate, moisture flow rate. So over time delta T, we will have this amount of moisture transport. And that moisture, and there is no generation. There's no moisture is not being generated inside the potato slide. We're not including evaporation inside the potato. If we had evaporation, it would be a negative generation. So because of this moisture going out, there is going to be a change in the storage of moisture in the potato. So that is written as change in the concentration of water. So here concentration is defined as moisture per unit mass of solid. So change in concentration of water, that of course has to be multiplied by the mass of dry solid. Okay, so simplifying and letting delta T go to 0, we get this equation. Okay, and this equation, you notice there is no x, there's no position variable, it's just a function of time. So the equation looks very simple, but to use it we have to be careful and go back to all the restrictions or the assumptions that we made under which we derived this equation. So let's look at the restrictions. So first thing is, we have no clue about the detailed mechanisms of moisture transport. We don't know how much of it is diffusion, if there is some pressure driven flow or so on. We have no idea about these mechanisms. So we are ignoring any pressure driven flow. We are ignoring any temperature changes. So you notice there is no temperature effect in there. We are also ignoring evaporation inside, and the boundary conditions like this sea vapor at infinity, it is not changing with time. If it is changing, we cannot use it. There's also the diffusional limitations, that it is true for like a small thickness or very high diffusivity. Either way, we have to check this Biot number for mass transfer to be less than 0.1. So it is very simple equation, but it is usable only only in very restricted situations. To solve this equation, note that these two variables are not the same. This is concentration of water, liquid water inside the solid, whereas this is concentration of vapor at the food surface. So we have to relate these two. How do we do that? We do that through what's called the water activity relationships. So in water activity relationships, these are measured from experiments. So you let a slice of potato come in equilibrium with surrounding air, and you get points like this that relate moisture in potato to moisture in air. So if I approximate it, linearize it, and then I can define, so this is my sea water, and then this is sea vapor, then I can define a quantity which would be K star. So this is 1, this is K star. Okay, so concentration of vapor divided by concentration of water, both at the surface, is related by this K star that comes from experimental measurement. It has to do with equilibrium between these two phases, the solid phase for water and the gas phase for water, which is the water vapor. Okay, so using this equation, I rewrite the vapor in terms of water. What does that do? Now we can solve it. Before we could not solve it because it's two different variables, water and vapor. So now both sides have water, so it's dc dt is equal to something times c minus a constant. So then the solution would be this kind of a exponential. Even though this plot has kind of overall the same look as average concentration or concentration versus time, when we assumed diffusion model or a more complex model, even though it looks similar to that, it is not to be confused. This plot should not be confused with those plots in diffusion equation. Here, the rate of change of concentration is only related to external factors, the rate of airflow or the temperatures and so on, because we're ignoring diffusion inside. Now I want you to pause this video and think for a few minutes, is this really a good way to describe drying? Meaning, this curve of concentration of water versus time described this way, is this really going to be valid for long time toward the end part of drying when moisture is going to be lower and therefore diffusivity inside is going to reduce? Is this still going to be a good description of drying? So think about that, and by pausing the video and then come back to it. So now we go for an even more restricted situation of drying, or an even simpler approach to drying. So let me explain how we got to this equation before we get into the details. When the material is very wet, its surface, which is very wet, that behaves a little like, or very much like, the surface of pure water. And the amount of vapor above the surface of pure water is given by the vapor pressure of the liquid, which is only a function of temperature. So then the vapor pressure above the food surface can be approximated by the vapor pressure above pure water, which is only function of temperature. So then at a given temperature, whatever temperature you're drawing, the amount of vapor is fixed. And so then this quantity, concentration of vapor at surface, is fixed. So this being constant makes the entire right hand side to be a constant. So then dc dt is constant, or concentration changes linearly. That's what we mean by a constant rate of drawing. So is this lumped parameter model for constant rate of drawing an empirical model? Not really. It is mechanistic, but it is applicable under a very restricted set of conditions. Now, if we plot the solution to the equation in previous slide, it's going to look like this. Moisture dropping linearly with time during the drying process. This constant rate of drying doesn't go on for too long because the diffusivity drops. Now the data here is shown for soil, not for a food material, but thinking of the food as a porous material, it has analogy with soil, and the behavior in food also has been described in analogous ways. So you see, as moisture is dropping, the diffusivity is also dropping. As diffusivity drops, then if we go back to our internal resistance, then if diffusivity drops, then this internal resistance increases. This whole thing increases as diffusivity drops. Internal resistance increasing or diffusivity dropping, what this means is now moisture is having harder time to get to the surface. It doesn't get to the surface as quickly as was assumed here. So then diffusion is starting to play a role. When diffusion is starting to play a role, then the rate will no longer be constant like here. So it will look more like this. So whereas we were here before, this part was here, constant rate, now the moisture is having this extra resistance inside, and it's going to start to have a falling rate, meaning the rate will keep dropping because now diffusion is playing a role, and diffusion the rate is dependent on the difference between inside concentration and outside concentration. So as the inside concentration drops over time, this difference also goes down. So in diffusion, we'll have a falling rate of drying, which is what happens eventually. Now, exactly where it changes from constant to falling rate, that is very, very material dependent. It's very hard to say which ones will have at what moisture content. For many food materials, the constant rate almost does not exist, or it exists for a very short time. So we start off at constant rate, but eventually uh, we start off at constant rate when it's mostly decided by the external resistance, but eventually it becomes uh, controlled by the internal resistance or a diffusion process, and that's when we would need to use at a minimum the diffusion model. To summarize, this lumped parameter approach to describing the physics of air drying being so simple, it may be tempting to use it more often, but we have to remind ourselves of all the assumptions that we made, all the limitations that it has. So let's look at them. So first of all, it is only valid when internal resistance is not significant as given by this ratio. So we plug in these values and check if this condition satisfies. Now, unlike diffusion formulas and so on, because it's not diffusion limited inside, it's really true for any shape. So for any shape, if you need to use this equation, we can approximate L as V over A, where V is the volume of the food and A is the surface area, and we can see whether the condition above this one satisfies, and then we can use it. Also, in this list of when we can use it, typically at early times when we derive this constant rate of drying, early times it's good for this lumped parameter description of physics because there's lots of water, and the diffusivities are higher inside, and the vapor pressure is more than likely to be constant on the surface. The other times that we can use, as again given by this equation, is when L is small or it's a thin material. So those are the times when we can use this lumped parameter approach. The physics limitations or limitations that come through the derivation, it's sort of an alternate way of discussing the same as to when we can use it. So first is this Biot number criterion has to be satisfied, which is typically for thin slices or small grains. Then drying airflow not highly turbulent. What this means is if it's highly turbulent, then external resistance is becoming small. And this lumped parameter approach is when external resistance is much higher than internal resistance. So in another way of looking at it is if this H itself is large, it will be hard to satisfy this equation. Also, when water diffusivity is not particularly low. So from a physics standpoint, those are the limitations for using this lumped parameter description of the physics of drawing. Typically, it is hard to satisfy. It is hard to satisfy this equation for drawing. So it is usable in kind of very limited situations. Can you pause the video and think of some situations where this lumped parameter approach of describing the physics of drawing is likely to fail? Now, that doesn't stop it being used very often. So it has been used quite often, but it often amounts to a very empirical way of using empirical way of describing drawing. So I'm not trying to name a product what can be used, because that can be misleading, because it does depend on a number of factors. So in these three frameworks for studying the physics of drawing processes, going from least to the most mechanistic approach, we just completed the least mechanistic approach to studying drawing process. If you are interested in a more mechanistic approach that includes the diffusion based modeling of drawing, diffusion based description, then you can look into the previous video. And the video before that can give you the most comprehensive description of drawing that even includes how we can calculate, for example, shrinkage, how we can describe shrinkage. So the next video in this series, which is the last one, would simply summarize these three frameworks.